All right, here again is going to be an area that's probably less familiar to everybody. Containers have been out for a while, and that's the first, but the Kubernetes service is really focused on very high-end applications. And so I just forewarn you, it's an area where there's a lack of familiarity. I'm not going to spend a lot of time with it because I saw how much time was spent on the exam, number one, and number two, I know, in real world situations how little we actually deal with this. Okay? And that's not to say that my experience is going to be the same as everybody else's experience, but being that I work for an MSP, we are the cloud provider for hundreds and thousands of individual clients. The stuff that I see on a daily basis varies all across all different kinds of organizations, all different sizes and whatnot. So I feel like it's a pretty good representation of what you're going to see out there in the real world, right? I mean, our company we have customers in about 10 different states. In various demographics and various types. I mean, all of those things, and it just kind of goes to say this isn't overly real world. Okay, it is real world depending on your scenario. You are going to be asked questions about containers and Kubernetes in the exam. It is just very minimal. Okay, I only remembered a couple out of the 55 or so questions on mine. Okay, so let's talk first containers. This is something that we need to get down conceptually. It just because it represents a further evolution of hardware virtualization technologies. Now, it is more of it's more of an app kind of related thing, so platform as a service, right? But we need to understand what this means just from an architectural standpoint, okay? So with hardware virtualization, we can run multiple isolated instances of an operating system on the same physical hardware, right? We all know that. We've been using virtual machines for some time. Containers are just the next stage of that. Container-based virtualization lets you virtualize the operating system itself, okay? Not the physical hardware, right? Doing this, it means you can run multiple applications within the same instance of an operating system, but have complete isolation between them. So instead of an entire virtual machine for one application, I just have a container for an application. It's all running within the same operating system instance. Okay, now that may still seem confusing. Let's talk about some of the differences. Okay, containers give you very lightweight isolation from the host and other containers. Now they do not provide complete isolation from the host operating systems and other VMs. Okay, so in some cases, you need a more distinct security boundary. You're actually going to choose virtual machine over container. Containers within the same OS. Okay, in a container, it doesn't run the complete operating system, user mode and kernel mode. It's only running user mode. And that can actually be tailored to contain just the necessary services for your app. And in that way, it's a little bit more secure, but it also provides you with the ability to use fewer system resources. Okay, virtual machines, they run a complete operating system, so they require more resources. We can deploy individual containers via Docker. Docker is a service, and you can use the command line, or you can use another orchestrator service, the Azure Kubernetes service, whereas with virtual machines, I don't have the ability to use Docker. Now here again, we're speaking of something that's not really necessarily my language. I mean, they started talking about it in Windows Server 2016 and 2019. It's kind of been there, but haven't really seen this utilized very much. It's really more from a development kind of standpoint that they would be familiar with using Docker. Persistent storage is provided for us via Azure Files. Okay, technically it's two different ways. You can use Azure Disk for local storage for a single node, or you can use Azure Files, which would be your file shares that are accessible via SMB. For that storage and fault tolerance, if we have it's automatic with containers. Okay, if you have a cluster node fail, any containers that are running on it are going to be rapidly recreated by the orchestrator on another cluster node. So there are a lot of advantages over physical and virtual machines. Increased flexibility and speed when you're developing the code and sharing it. Simplified application testing. Streamlined deployment and improved resource utilization. Again, the vast majority, if not all of those statements, really not overly relevant to an ongoing administrator, right? It's more from the development side of things. So now that we know a little bit about what containers are for, let's talk about some of the other fundamentals, because these are, for cloud applications, these are becoming the preferred way of, packaging them up, deploying them, managing them, and it's just a very quick way for us to do it without virtual machines. So it is very efficient, okay? It just kind of depends on your role as to what part you play in this, but we still need to know. So container instances are a great solution for any scenario that can operate in isolated containers. Okay, so these would be like simple applications, task automation, build jobs, things like that. They have very fast startup time. They can start up in seconds without the need to provision and manage virtual machines. They support public IP addresses as well as FQDNs, DNS names. We've got custom sizes, so they can be scaled dynamically to match exactly what you need in terms of resources for an application. They support persistent storage, the direct mounting of Azure file shares, as we mentioned. And then there's platform compatibility. So these can be Linux and Unix. In fact, you can have multi-container groups that share host machine resources. They can be deployed into Azure Virtual Networks, would be another feature of container instances. Container groups is going to be the top level resource in container instances. So a container group is a collection of containers that get scheduled on the same physical host machine. So they share a number of things like lifecycle, the resources, your local network, your storage volumes. Okay, they share all of that. So it is going to be scheduled on the same host, assigned a single DNS label or name, exposing a single public IP, and then you can use them to have divided functionality, multiple manageable containers. Okay, so for instance, one container listens on port 80 while another container listens on port 443. All right, but they're all managed within the same group. These can be deployed as a resource manager template or as a YAML file. YAML is a very concise format, and so that's recommended if the deployment includes only container instances. The templates are recommended when you need to deploy additional resources within Azure, like VNets or storage or things of that nature. Now, Docker, we mentioned earlier, well, that's the platform that provides developers with the ability to host applications within containers. Docker is available for both Linux and Windows, and it provides a guarantee that containers and their software will always run the same. Okay, Docker's the platform. Developers are the ones hosting applications within containers. Container is a standalone package. And that package contains the code, the runtime environments, system tools, settings, configuration files, and those kinds of things. Okay, Docker provides this guarantee. It's always going to run the same. It doesn't matter if it's run locally on Windows, Linux, or in the cloud in Azure. It's developed locally within a container, can be shared out for testing, and then deployed in production. All right. Now, what are some of the terminology terms that we need to be aware of? Well, container, an instance of a Docker image. So that's a single application, a single process, single service. The container image refers to the actual package, the software package with all its dependencies and information that would be required. The build refers to the action of building a container image based on a bunch of information that you've provided, and this is provided in what's called a Docker file. Pull would be downloading a container image from a container registry, and push would be uploading. And then the Docker file is a text file that has all the instructions on how to build a Docker image, kind of like a batch script. Defines the image and defines all the different actions that are going to be a part of the build process. Now, the next option that we have is the Kubernetes service, and this is an open source system that was developed to automate deployment, scaling, and management of containerized applications. The key word is orchestration, and anytime you see the word orchestration, we're talking about automation. You have an orchestrator system that is automating the process of deploying resources, in this case, deploying applications within containers to production cloud environments and all of the little interdependencies that would go along with that. Okay, now this is a fairly large topic. This was an orchestration system that was originally designed by Google. It is heavily used with microservices applications. However, if you go and search for what a microservices application is, you will find examples of Amazon Prime, Netflix, Apple TV. I'm throwing that out there as another streaming service, but these very high-end worldwide applications, okay? Twitter, TikTok, Facebook, all of these, the apps that are provided with these are often developed and managed this way. So here again, we have an area that's, really large from a deployment or from a development standpoint, and how much do we actually need to know on a daily basis about the Kubernetes service? I'm going to go with the vast majority of us don't need to know very much. It's represented on the exam, but it is, as I said, very minimal. So we're going to just try to get some of the terminology down and try to understand kind of how it works. But just remember, the overarching goal here is we're supposed to be able to have integration between applications and services in an open platform, and Kubernetes is providing that automated integration. So Kubernetes is going to define the control plane, and basically this is, just think of it as, think of the master as the main controlling unit of the cluster. Okay, so it directs communications across the system, it manages workloads, and the control plane is what's responsible for that, and it's actually got a lot of different pieces. Now, again, not all of these are going to be testable, but you have the ETC daemon that is a system that is trying to favor consistency over availability in the event of network issues. Okay, so it's monitoring the rollout of this application across cluster nodes. You have API, the API server, which is another kind of key component. It processes and validates requests and updates the status of those in the main ETC daemon, the scheduler, and then the controller manager. Okay, scheduler is a pluggable component that is responsible for selecting a particular node that is going to host what's called a pod, which we'll get to in a second. That's an application, basically, or a grouping of containerized components, which are applications. And so the scheduler is determining which machines that will go on, and then controller manager is actually, it's making sure that all of the resources that are chosen are actually available. The nodes, these are also known as a worker or a minion. This is basically a machine where the containers are actually deployed. So these are nodes in a cluster. They'll all contain the runtime as well as Docker, But then you have a kubelet, which is responsible for the running state of each node, making sure each node is healthy. The kube proxy is an implementation of a load balancer. And then the container runtime, the container resides inside the pod. The container is the lowest level of the microservice. It holds the application, holds all of the libraries and any other dependencies. And then pods are the basic scheduling unit. Okay, so a grouping of containerized components. Each pod has its own unique IP address within the cluster, which allows applications to use ports without having any conflict, and they are isolated from one another and can define not only the application but also the potential dependencies. Some additional terminology. We have pools. Pools are groups of nodes that have the exact same configuration. Nodes are, of course, the individual virtual machines, as we mentioned, running the containerized application. So you can have a pool of nodes. Pods are the individual instance of the application. Okay. Then we have containers. Containers are that lightweight, portable, executable image. It's got all the software, all of its dependencies. The deployment is one or more identical pods managed by Kubernetes, and the manifest is that YAML file that is describing the deployment of the application.